Hello students, I'm going to go to full screen here. I'll bring it up. Testing 1, 2, 3. Hello, students. Okay, we're going to go now to infrared. So I'm going to scroll ahead here. I'm using PowerPoint slides from a different textbook, the 6th edition, Paula Bruce's book, which I used to use. Incidentally, in January, I'm going back to her, I believe it's 8th edition. There's an e-version, which is also available for students at a cheaper price. Periodically, every 4 or 5 years, I look at changing books. Keeps me on my toes. All right, now, we're going to come in right at this point, and I'm going to go to full screen. Spectroscopy and the electromagnetic spectrum. Spectroscopy is the study of the interaction of matter and electromagnetic radiation. So we're going to focus on infrared right now, and energy from the sun that reaches the Earth's surface is visible light, heat, which is infrared, and a small amount of ultraviolet light, which can cause skin cancer, of course. These solar panels, they focus on visible light, but some of them are focusing on the harvesting infrared radiation. Organic compounds, compounds that have permanent dipole moments, will absorb infrared. More about that in a minute. But I want you to see right away, short wavelength, high frequency. Low frequency, long wavelength. So shorter the wavelength, the more energy is involved. So there's your wavelength. You study this in physics. And the de Broglie relationship, and you see that wavelength and frequency are inversely proportional. Now, we use in infrared a term, a value, wave number. And that's actually reciprocal frequency, and it's another way to describe the frequency of electromagnetic radiation. And in infrared, that's what they use. Most infrared people are using reciprocal wave numbers, reciprocal frequency. But some do use the wavelength in microns. I use wave numbers myself, but normally you'll see both on a spectrum. Singular spectrum, plural spectra. Now, high frequencies and short wavelengths are associated with high energy. Vibrational transitions are observed in infrared spectroscopy. Infrared, like NMR, radio waves next week in the summer session here, is quantized. And the quantum leaps are very small with vibrational and in NMR rotational modes. They're quantized, but the packets are small compared to ultraviolet light with electronic transitions, which are much larger. But keep in mind that infrared is quantized. Now, two modes that you want to retain at this point in a very basic introduction. You have stretching vibrations and bending vibrations. Now, the stretching usually is at higher frequency, shorter wavelength, and bends are normally over to the right in the spectrum, as you'll see, of longer wavelength, lower frequency. Now, I want you to remember there's symmetric and asymmetric stretches. And for bending, there's actually 4 different modes. Symmetric in-plane bend, called scissor. Then there's asymmetric in-plane, rock. Symmetric out-of-plane, twist. And asymmetric out-of-plane, wag. 4 bending vibes, 2 stretching vibes. Functional groups, this is important, of course, in organic, stretch at different frequencies, and infrared spectroscopy is used to identify the presence of the functional groups that you've been studying week after week. Alkenes, alkynes, alcohols, aromatics, carbonyls, right? How they're prepared and how they react. Infrared transitions require a bond dipole to occur. So, for example, carbon tetrachloride, CCl4, does not have an infrared because there's no bond dipole. Of course, there's a lot of theory behind this, and there are some that focus on experimental use of infrared, experimentalists and theoretical chemists that study infrared at a higher mathematical level. But you have to have a bond dipole for an infrared. The more polar the bond, the more intense the absorptions. So if you consider an OH versus an NH versus a CH, the CH is the least polar sigma bond. It's the least intense. Oxygen more electronegative than nitrogen. So compounds containing an OH, carbon compounds with an OH, an alcohol functional group, are the most polar and will be, of the three, the most intense. The intensity of an absorption band also depends on the number of bonds. So for example, if you're comparing a C10 hydrocarbon decane to a C4 butane, well, you have a lot more carbon-hydrogen single bonds. So in the former, so the intensity will depend on the number of bonds. So the more carbon-hydrogen bonds you have, the larger the band will be that you see. Influence of symmetry on infrared activity of the alkene stretch. So what we see here is a comparison of 1-butene, 2,3-dimethyl-2-butene, and 2,3-dimethyl-2-heptene. So asymmetric about the carbon-carbon bond, the one on the left there, 1-butene, it has a dipole moment. The one in the middle is symmetrical about the carbon-carbon bond, symmetry. Not a meso compound, but there is a symmetry and plane of symmetry, and it has no dipole moment. Then the one on the right will have a slight, it will have an infrared because it's slightly off kilter with the N-butyl group attached, versus the one on the left, which has the 3 hydrogens. But the one in the middle you see is symmetrical. It has no infrared. The other two do. That's my point. 1-butene, infrared active. 2,3-dimethyl-2-butene, infrared inactive. And 2,3-dimethyl-2-heptene, infrared active, but very weak absorption band, because there's only that very small difference there with the N-butyl versus a methyl. Now, the vibrating bond is a quantized harmonic oscillator. That's the term used. See, infrared is actually obeys Hooke's law. We can view it as a ball and spring model. So if you have hydrogen chloride in the gas phase, in water it's hydrochloric acid, hydronium ion and chloride, but in the gas phase, you can consider that sigma bond as a ball and spring model. A hydrogen, a chlorine, ball and spring. And then what we're going to do is do a stretch. We're going to do a stretch vibe. So quantum levels for a stretching vibe can be shown in this diagram. A plot of energy versus the directional plane of the HCl. And you can see that you have the different vibrating modes. They're quantized, small packets, but nonetheless quantized. And of course, you keep stretching until you break the bond. Fundamental transition that we're going to look at would be the initial V0 going to V1. Ground state, and you get to the right wavelength. Then overtone is when you go from V0 to V2. And of course, you've heard of harmonic overtones in music. They can have beautiful sounds. And indeed, you can also apply stringed instrument theory, physics to stringed instruments. Overtones are twice the frequency of the fundamental transition, and they're always weak. We'll see them from time to time in the infrared spectra. Okay, here's Hooke's law. The approximate wave number of an absorption in a compound for a functional group can be calculated from Hooke's law. V equals 1 over 2 pi c times the square root of K over the reduced mass. So if you're looking at an HCl, M1 would be H, Cl would be M2. It would be 1 times 35.5 for chlorine. And it would be then 1 over 35.5 0.5. C is the speed of light, that's a constant. Pi is a constant. K is the force constant, and that depends on whether you have a single, double, or triple bond in the functional group, and that's dynes per centimeter force. But that's Hooke's law. And that predicts that lighter atoms will vibrate at a higher frequency. They'll be over to the left in the spectrum than the heavy atoms. For example, a CH stretch for that sigma bond be about 3,000 reciprocal centimeters. We could calculate that. For a deuterium replacing hydrogen, it'd be 2,200 because deuterium's heavier. A CO stretch is going to be 1,100 because oxygen's a lot bigger. And then CCl is all the way over to the far right, 700 reciprocal centimeters, because the chlorine is so much heavier than hydrogen. Increasing the S character of a bond will provide a higher K value, and it increases the stretching frequency. Table 12.5 from the 6th edition of Paula Bruce shows you something of practical use to us. Infrared absorptions of carbon-hydrogen bonds. You have the triple bond CH, double bond CH, tetrahedral CH, and a hydrogen bound to a carbonyl. A carbonyl is a carbon-oxygen double bond, a sigma and a pi, and there's 2 lone pairs on the oxygen not shown. That's an aldehyde functional group. Well, what we see with wave numbers, for a triple bond carbon H, it's about 3,300 where that stretching frequency, that vibration, stretching vibe will be seen. For sp2 carbon, it would be slightly to the left of 3,000, 3,100 to 3,020. If you don't have any unsaturation, no pi bonds, then an alkane would be about 2,960 to 2,850, and the aldehyde actually exhibits 2 stretchings, symmetrical and an asymmetric, one at 2820 and the other at 2720. So you can always tell with aldehydes because you'll see for the CH 2 absorption bands. SP, SP2, SP3, and SP2 are involved. Here's a handy table which is very good for you in a brief introduction to infrared. This table 13.4, you note the influence of mass and S character on stretching frequency. There you see all these different functional groups that you're eventually going to be studying. Carbon-nitrogen triple bond, carbon-carbon triple, carbon-carbon double, carbon-nitrogen double. Aromatic is their hexane ring with 3 conjugated double bonds. CO double bond, CO single, CN single, alcohol is OH. Then you also have carboxylic acids, which have a carbon-oxygen double bond and a COH single bond. Then NH for amines, and then CH. Very handy table, and you have the wave numbers there, and you also see the intensities. You see they vary depending on the polarity, the electronegativity of the atom involved. Here's a typical infrared. Over on the left of the spectrum is high energy, and way over on the right is lower frequency, low energy. Your wave numbers are at the bottom, and they generally run from 600 to 4,000. And then you have your wavelengths from 2.5 to 16. The functional group region is generally from 4,000 to 1,400. And the fingerprint region is about 1,400 down to 600. That's called the fingerprint region. And if you have 2 compounds that have 2 unknowns, and their fingerprint regions perfectly overlap, well, they may be one and the same. Excuse me. Now, here are 2 constitutional compounds. One could be called 2-pentanol, and the other's 3-pentanol. The functional group regions, both compounds are alcohols. Look at the fingerprint regions. They are different if you study them very carefully. For example, you see this band and this one? You can see the scissor on this one, and it's not appearing here. we can differentiate between these two constitutional isomers. Incidentally, you see this big broad stretch there and there? That's your CO, that's your OH stretch, alcohol stretch. These are your hydrocarbon stretches. Note there to the right of 3000, no pi bonds. sp3 carbon H stretches. Same there. The exact position of the absorption band depends on electronic delocalization, the electronic effect of neighboring substituents, and hydrogen bonding. Resonance and positive or negative induction, good or bad neighbor effect. For example, on the left we have 2-pentanone. That carbon-oxygen double bond with 2 lone pairs on oxygen not shown shows up textbook about 1720 reciprocal centimeters. That's called a ketone. See the ending? The suffix ONE. 2-pentanone means it's a 5-carbon ketone. Now over here on the right we have 2-cyclohexenone, and that's a conjugated system. See, carbon-oxygen double bond, double, single, and then another double. That's conjugated. There's resonance. See the arrows? So as a result, that moves down to 1680 reciprocal centimeters for this carbon-oxygen double bond. In other words, resonance is stabilizing, and you get a dramatic shift to the right towards longer wavelength, more stable. In other words, that carbon-oxygen double bond from resonance contributor 1 to 2, there's single bond character because of resonance contributor 2. This is called an overtone, and some carbonyls will exhibit that. Now, you never run an infrared on a compound that has contact with water if it's wet, because if you're using potassium bromide plates to run a thin film, let's say you have a high boiling liquid and you want to run the infrared, you would smear it on a potassium or sodium chloride or potassium bromide plate, because they're transparent, the latter, and get the infrared as a thin film. But you never run a compound unless it's been dried with calcium sulfate anhydrous or magnesium sulfate anhydrous, because the water will show up because it has OH stretches, OH bonds, but the water will dissolve those plates, the sodium or potassium bromide, sodium chloride, potassium bromide. So you always have to have a compound free of water. If there were water, it would have a big broad stretch there. That's not water, that's not an impurity, that's a carbonyl overtone. You studied that at a higher level. Okay, this is an ester, and that's a carbon-oxygen double bond, CO single, OC single. That's an ester functionality. Arguably the most important functional group in industry is the ester in compounds of commerce. There's your carbon-oxygen of the ester. That's about 1735 reciprocal centimeters. And there is the CO single for this one. There and there, symmetric, asymmetric. And ketones have only a carbonyl stretch. See, because they don't have the CO single on this side. There's only one oxygen. And this is a conjugated one. So that ketone has moved down to around 1680 or so. Putting an atom other than carbon next to the carbonyl group causes the position of the carbonyl absorption band to shift. So here on the left, we see the resonance electron donation. Z is able to move a lone pair of electrons in resonance. That gives you single bond character. But if you have a highly electronegative group, Z, let's say fluorine or chlorine or bromine, well, they're not going to want to share readily. They're pulling electrons away. That's called negative induction, and you won't get that single bond character. But if you have somebody that will donate electrons, maybe a nitrogen with a lone pair, then you're going to get single bond character, and that's going to cause changes in the absorption band where it shows up. The predominant effect of the nitrogen of an amide, that's when you have Z as nitrogen, is electronic donation by resonance. Nitrogen apparently will share its lone pairs in resonance, giving you carbon Z double bond. resonance contributor 2, and more single bond character for CO. The predominant effect of the oxygen of an ester is inductive electron withdrawal. Oxygen does not want to share as readily. It's more electronegative, so you're not going to be getting any of this delocalization that you're seeing with Z equal nitrogen. Here are two compounds. This one, the top one, is an ester. There's your carbonyl stretch of the ester, which they tend to be about the middle of the graph, and very powerful stretches. And then you have your CO single bond stretches. And then for this amide, this is a tertiary amide because the nitrogen is trivalent, but it doesn't have any hydrogens. It has two methyl groups. That's a tertiary amide, and you get this very powerful carbon-oxygen amide stretch, and that's going to be generally around 1680. Around 1680. The ester up here is around 1735 reciprocal centimeters. The position of a CO absorption varies because of resonance release in carboxylic acids and esters. So in other words, the functional group, here's an alcohol, ethyl alcohol. That's about 1050 for the CO stretch. The OH stretch is way up around 3300, a big broad stretch as I mentioned. You'll see it again. Now here, this is diethyl ether, so you have CO on both sides, and that's about 1050. But now look at this next one. Here we have acetic acid, a carboxylic acid moiety, and we see resonance contributor 1 and resonance contributor 2, and an unshared pair on that oxygen, there are two, can delocalize in, giving single bond character to that carbonyl, and that'd be about 1250. Because in carboxylic acids, the oxygen can delocalize because there's two oxygens. That'll take you to 1250. Then with the ester, that's going to be about 1250 and even 1050. So you're going to see not so much resonance as here, the third example, but you will actually see a little 1050 showing up with that ester versus the carboxylic acid. These are subtle things. Okay, this is an alcohol, and notice you have 6 carbons. So that would be called 1-hexyl alcohol, or hexanol, N-hexanol, straight chain hexanol. So you have a big broad OH stretch, characteristic of water and alcohols. But then if you have 5 methylene units or more, CH2 units, you get this little blip there. I'm not sure, most people don't know why. I guess theoretical people would know. But if you have a chain with 5 or more CH2 units, you'll get that blip. So C8 would have it, but C4 would not. And then, of course, there's your CO stretch, single bond stretch. 1050. Carboxylic acids are readily distinguished from alcohols. A carboxylic acid here, this is your, acetic acid. Well, here we have 1, 2, 3, 4 pentanoic acid. And what you're seeing is the 2 OHs, and it's very jagged. See this? They call it a bearded infrared. And you can see this broad movement that alcohols don't have. And then you have the CO double bond stretch for a carboxylic acid around 1700 reciprocal centimeters. And then the CO single bond, which is going to be down around 1050 or so. Higher frequency CO stretch, because you don't get as much double bond character, so it's going to be higher frequency there. And that's the broad OH stretch of the carboxylic acid that extends way over to this side. The position and breadth of the OH absorption band depends on the concentration of the solution. So if you're putting an alcohol into a solvent like carbon tetrachloride, which is infrared inactive, that concentration will affect the qualitative appearance of the infrared. If you have a very concentrated solution, you're going to get heavy-duty hydrogen bonding, and you'll get 3550 to 3200, a very broad band showing up. But if you dilute that solution and don't have hydrogen bonding, it'll sharpen to 3650 to 3590. So how you prepare that sample will change the appearance of it because of hydrogen bonding. Now here's an important table, 13.5. Infrared absorptions of carbon-hydrogen bonds. As I mentioned before, you can have triple bond carbon H, double bond CH, single bond sp3 carbon H, and aldehydic sp2 carbon but aldehyde H, which gives 2 bands. Now look down here. Trans, alkenes, Z, cis, Zusammen. We can differentiate between cis and trans geometric isomers in the infrared. The most valuable technique for knowing right away if you have cis or trans in an alkene is to run an infrared, because you can detect as little as 0.5%. Now, you know how they talk about contains no trans isomers with potato chips and other things because of the catalytic hydrogenation? Well, if you contact a cis alkene with a cheap catalyst like nickel instead of platinum or palladium, that catalyst with heating can isomerize and convert the cis into the generally more stable trans alkene. But the cis double bond is natural in fatty acids that are unsaturated. Trans isomers are not natural and they take longer to break down. They're less biodegradable. So you can tell if frying oil with that heat, the natural vegetable oil, cis, has isomerized to any extent to give trans. Then you can see if you have a tri-substituted alkene, terminal alkene, disubstituted, or terminal alkene monosubstituted. Very handy table. The strength of a CH bond depends on the hybridization. That's for the top part. Now, examine the absorption bands in the vicinity of 3,000 reciprocal centimeters. And what we see here is a cyclohexane with a methyl group. They're showing it as a planar. You know it's a chair with methyl, generally equatorial. You won't see the difference between equatorial axial normally in the infrared. And right now you just focus on the structure itself, not the conformation. You have the sp3 carbon hydrogens to the right of 3,000. You have a CH there. That's the H not shown in this structure. And then you also have a methyl group. You can detect the CH3 methyl group. The bottom one is cyclohexene, and there you have a carbon-carbon sp2, and those H's attached, those CH's, are going to show up to the left of 3,000. That means you have unsaturation if you see infrared band immediately to the left of 3,000. And there's your saturated portion on to the right. And also you get a carbon-carbon stretch, about 1660. It can vary, but it can vary from weak to moderate. So here it's the CH, sp2 carbon CH, and this is the carbon-carbon sp2 carbon-carbon stretch. Then there's a CH bend. See, bends are over here, stretches are higher frequency, shorter wavelength to the left. This is an aromatic compound, and that's studied in McMurray in the second semester of organic, and that would be ethylbenzene. The benzene being that 6-membered ring, an aromatic it's called that, and you see why later in the course. There's conjugation here of the 3 double bonds. This is called an arene, A-R-E-N-E, an arene. Arenes are benzene rings with alkyl groups on them. Very important. And boy, oh boy, look at the absorption bands. Now here, do you see these 4 fingers? 1, 2, 3, 4. If you look very carefully at that, that can often tell you the pattern of substitution on an aromatic ring. A monosubstituted, a benzene ring where there's an alkyl group instead of a hydrogen. The other points are all hydrogens not shown. That will give this band. That's an overtone pattern. And then there's your CH3. There's your CH, and then also the carbon-carbon stretches in the benzene ring, as well as to the left and right of 3000, because you also have alkane and aromatic ring. Benzene ring, sharp absorption bands at 1600 reciprocal centimeter and 1500 to 1430. Overtones at 1700, 1900 reciprocal centimeter for the in-plane and out-of-plane benzene CH bends. That's 1700 to 1900. 1700 to 1900. Very diagnostic. The benzene overtones are in the diagnostic region and readily recognized. And it can tell us the substitution pattern on that benzene ring. And there's your benzene in plane and out of plane CH bends. Way over to the right, bending, stretching over to the left. Aldehydes. In aldehyde, you study all the carbonyls, carbon-oxygen double bond scenarios, ketone, aldehyde, carboxylic acid, ester, anhydride, amide, acid halide. All of those are studied organic too. Well, don't forget the aldehyde now is going to have those two bands for the CH stretches, symmetric and asymmetric, of an aldehyde. And an aldehyde also has a very powerful carbon-oxygen bond, the aldehyde. Ketones, aldehydes are very powerful carbonyls. And you can identify a functional group by the bending vibes. Now, here's an amine. An amine, not an amide. There's a difference between amide and amine. An amide has a carbonyl there too, carbon-oxygen double bond. Amines do not. Organic amines are very important compounds in biochem and in drug syntheses. So for this primary amine, that's a nitrogen with two H's and then this big alkyl portion. There's your NH stretches. Less powerful than oxygen because oxygen's more electronegative than nitrogen. And then you have your NH bend. And there are these two CH3s that are showing up right there. Primary amine, two NH stretches, symmetric and asymmetric, around 3350. There's also an amine NH bend. This compound actually has a poor man's isopropyl. It's not really an isopropyl, but there's an isopropyl built in if you want to look at it that way. And that split at 1380 indicates you have an isopropyl built in. This split. Analyzing an infrared spectrum, or more than one spectra, the position, intensity, and shape of an absorption band is very helpful in identifying functional groups. The absence of absorption bands can be useful in identifying a compound in infrared spectroscopy. Bonds in molecules lacking dipole moments will not be detected. I mentioned that already. Okay, here's a simple alkene, and you can see you have unsaturation to the left of 3000. Simple alkene. So you have a 3075, that's your sp2ch. 2950 is sp3ch, to the right of 3000. 1650 and 890, terminal alkene with two substituents. You have less than 4 adjacent CH2 groups, so you won't get anything there. Pretty simple, but you can tell it's an alkene right away. This is benzaldehyde, a very important naturally occurring compound, benzaldehyde, a benzene ring with an aldehyde group attached. And they assign 3050 as the sp2 carbon hydrogen stretches, 2810 and 2730 an aldehyde, 1600 and 1460 is your benzene ring, 1700 is a partial single bond character carbonyl. So there's resonance. That double bond can move right out and give you single bond character for CO. So that's about 1700. Normally it's about 1720 for aldehydes. This is called propargyl alcohol. This is a compound with a triple bond and a primary alcohol. A primary alcohol is an oxygen bound to a primary carbon, hence a primary alcohol. So you can see right away the OH. And in this region, about 2200, there's not too much that shows up there. You know, like the Milky Way at night, there are parts of the heavens where there's virtually not a lot of star density from our point of view on Earth. Well, the same with 2100, 2200 reciprocal centimeters. That's where you find triple bonds and nitriles. A nitrile is R bound, single bond to carbon, bound to nitrogen, triple bond, nitrogen with lone pair. Organonitrile. And nitriles also show up around there. But that's your triple bond carbon-carbon. Tends to be weak to moderate. It's assigned 3300 for OH, 2950 for sp3 carbon, and 2100 is your carbon-carbon alkyne, sp-sp, stretch. This is a secondary amide. That's a nitrogen that only has one H. A primary amide has two H's. A tertiary amide has no H's, just alkyls. This is called N-methyl acetamide. And you can see the assignments here. 3300, 2950, 1660, and 1560. And see, you're already picking up 4 bands now. You're starting to look at infrareds and pick things out. NH, sp3 carbon H, amide carbonyl, and NH bend. Now, the amide carbonyl has a lot of double bond character through resonance. So that's why the amide carbonyl is way over to the right, because it's actually the most stable carbonyl, the amide specifically. More about that in Organic 2 lecture. Here is a ketone, aromatic ketone, but notice the carbonyl, the ketone, is not conjugated with the aromatic ring. It's separate. It's by itself, see? So that's non-conjugated. So that's going to show up right where ketones do. Generally 17, 15. What are they telling us? 17, 20. Okay. There are your assignments. And that's all I want to show you with infrared. There's much, much more to this. Much more. On an MCAT, a GRE, PCAT, DAT test, national test, if they're testing you on knowledge of organic, they may just show you an infrared spectrum and say, what is this? And you would say, oh, all right, I studied enough to know that's an infrared. You'll be able to differentiate between NMR, infrared, and mass spec by the qualitative appearance of the spectrum shown to you or graph shown to you. Okay, guys, thanks for watching. Bye for now.